So welcome to this afternoon session. Basically, the themes around data science and applications in oil and gas. Our first speaker is Ted and Lee from Preview A&M. And the floor is yours.
Okay. All right. Thank you very much. Yeah, it's really my pleasure to presenting our work at the REST conference again. So this is a work we recently worked on with Ted, and we worked together on this solving the wave equation problem. We're using a PiTorch, basically using a deep learning software platform. So it is not really data science method. It's really using data science software to solving a problem with reformulate the wave equation using the recurrent neural network model. Okay, so so this is we talk a little bit about this. So we give an introduction. We talk about the this is really what we want to talk is the data science and the scientific computing. They are two different areas, two different subjects. However, we know that data science has been very successful in many areas, and we want to see, can we bring them together? Especially scientific computing, we know that there's so many things in this area as we're using high-performance computing to solve those kind of problems. The previous keynotes talk about the CFD, and here we have the wave propagation, inversion problem. We are using HPC resources to solve those kind of problems. So there are some similarities I want to talk about that, although they are very different in the sense that data science are mostly based on statistics and probability kind of method, where those kind of physics solution with HPC, scientific computing based on physical principles. So they are very different in terms of the methodology in principle. However, there are some similarities we want to see that is this, for example, we know we solving using numerical methods solving this kind of problem. So it's kind of, it's like a lot of things are optimization problem. If you think about that perspective, data science and like inverse problem, they all, overall, they are inverse, it's all optimization problem. So we try to, that sense, they are kind of similar in this sense. So if we can remodel or reformulate the computational science problem with a data science neural network, we are able to solving using the advantage of the deep learning software and to solve a scientific problem. In other words, we'll be able to possibly to bridge these two domains together. So this is one thing I want to say that, yeah, do not throw the baby out with the bath water, because we have, for the research community, there are so many efforts, decades effort to building this, scientific computing. There are some methods currently used, pure data science, method to solving this problem. However, we see this kind of sorry for doing that, because we kind of throw the baby out, because there are so many good things in the scientific community. We want to preserve that. For example, a lot of things are, scientific problem are under constraint, for example, and there are some theories, a lot of theories based on the physics, so that we want to utilize them to see if we could possibly help each other in this case. So we want to talk about this is a full waveform inversion problem. I know probably this is very familiar to this community that is using for seismic topology, tomography, and that's try to solving this using from model domain to data domain. That's a data capture, and we go backwards to figure out that's how we can find out the model using inverse problem. So this is really based on physics of wave propagation. That is a wave propagation solution. Traditionally, people try to solve this kind of equation here, right, PDE. And this is a simple case. It's a 1D PDE, and that is a second derivative. Try solving this based on the t and x respect to that. And what we're trying to do is to say, can we formulate this problem with the recurrent neural network? This is actually not new. This has been done by other researchers. Actually, I think the first one is Alan Richardson. He actually had this kind of work like 2 years ago. He had a paper talk about this using TensorFlow. So we're trying to use PiTorch, and this have some other approach. We're trying to merge. We use PiSit. We'll talk about that. And so this case, we will try to see, actually, if you think of recurrent neural network, it's actually exact same thing is this, we try to solve this PDE with the time steps. Recurrent neural network is try to figure out what's the status for next time step. We're doing the same thing when we try to solve in this PDE, use a finite difference or finite element method. We're trying to do the same thing. We're trying to solve its next time step. What the status will be for next time step, right? So it's very similar in that sense. And also, one thing we can say is, if you can formulate this problem with iron, one thing would be say is there are built-in automatic differentiation inside PiTorch or TensorFlow, all of this deep learning software. We'll be able to utilize that to calculate the gradients, which we can apply all the gradient-based optimizations easily. And they all have been built in this PiTorch or TensorFlow software. So be able to apply them. We can choose what's the maximum, what's the best solution we can have. And then we can use them to say there are a lot of optimizers we can use. So there's quite an advantage for that. And so what we can do is, this is the one way we actually formulate this problem. And with this recurrent neural network, if you can think about that, we can reformulate this. This is a neural sire. If you think about that, this is a function. We can redefine it. If we refer to our paper, we can have a little bit, mathematics to figure out what this f really means. So that is the function you can go in. It can have two inputs, actually two hidden stators. So which means that we try to have this previous and the previous one, and be able to use both of them to be input to the current one, plus the current, the source, the f is the source, so that we can get the status for the current, the time step. So we can produce this kind of projection function to get the trace data on that time step. So if you think about this is a recurrent neural network, every single cell is trying to calculate the time step, the status for the next time step. So this one we can be 1,000 of them, or be longer than that. We'll calculate all this, every time step we can get the status. So this is what we can have. So another thing we can do, as I said, we can use the auto differentiation method building inside the PiTorch. It is not finite difference, which means it could be more accurate. We know traditionally we'll use the A-joint state method to calculate that and to calculate gradients. And this way this could be more accurate because it's really it's every single operator. We try to record it and figure out what's the derivative for that for this every operator. So we try to do, this one can use it to calculate a list of the operations. And based on the chain rule, you'll be able to figure out what's the gradient in respect to any variable you need to do. So that is the auto differentiation method. So this is some kind of results. We want to show that also for 1D case. Another thing we want to say is it can utilize the GPU. It's very nice to see that because we don't have to spend time to convert the code to CUDA or OpenCL or some other language that utilize GPU, because this had already been built inside this PiTorch software. So be able to utilize GPU to get a better performance. So this is the one case we try to do. That this case we have this is our model, and this is our initial model. And this is go over 100 iterations. We'll be able to get the performance, the inverted model. And this is a comparison. This is a comparison with the trace comparison. This is the observed trace and the simulated trace from the iron neural network. So you can see it's really hard to tell the differences from here. And this is the wave field. So there we have some differences, but in this inverse problem, this is actually a bit happy to see this kind of accuracy. Okay, so here with PiSit, would like Ty to talk more about this topic here.
So we were looking for a platform in which we could do our experiments and research, and we discovered this one, PiSit. That's a seismic imaging toolbox, and it was generated at MIT by these two researchers here, Russell Hewitt and Laurent Demenet. This is all Python, and well, I say it's all Python. Some of their stuff is C++ behind the scenes, but it's a Python's structure. And what we liked about this was that it's got everything is very modularized and highly structured. We've got core modules for defining the domain and the mesh and all the guts of the package, and then there's separate modules for receivers and sources and shots and acquisition for a whole survey. Those are all separate pieces. And then for actually doing the computations and the inversion, they've got a wide array of solvers. There's all different cases, elastic, acoustic, constant density, variable density, just a wide variety, and in multiple dimensions, 1D, 2D, 3D. And so it's very nice because you can develop your stuff in 1D, and then there's so much common code that it's easy to extend to additional dimensions just by using much of the code that you've already played with. So and there's also a selection of optimizers and objective functions, and these are all descended from specific base classes, and so there's lots of convenient inheritance and so on. It's designed quite carefully. So if anybody wants to try that, I recommend the path that we took, which was to do the little exercises ahead of time that they provided, and you saw the result of some of that in the 1D case that we did previously. So let's can I have the next slide, Renee? Okay. So what we have done is taken a lot of the computation that they had in using NumPy arrays, and in order to get it into this PiTorch framework, we sort of shadowed a lot of those array operations with tensor operations instead, and then we just say, okay, now we just specify the CUDA device instead of the CPU device, and it kind of theoretically it just happens. There's the devil's always in the details, but it's coming along. One of the things that allows us to do is PiTorch comes with its own set of optimizers and loss functions or objective functions, and we have incorporated those into this same inheritance framework that PiSit already has. So we've basically fitting that stuff into the PiSit architecture. So that was reasonably easy to do as well. And by going to those tools, we were able to use the RNN, the recursive neural network tools that are there in PiTorch. And so we did that wave equation implementation that you saw the pictures of. We've put that into this package. So, and here's one of their demo cases. It's just
You need to wrap it up. We have 5 minutes.
Okay.
So jump to conclusions, please.
Okay.
So.
Okay, we can jump to.
Oh, that was the 5-minute warning?
Yeah.
Okay. Yeah, I'm almost done here.
Okay.
Come on back for just a second. So where we are with this, yeah. So this was their example. It's a 2D calculation of a flat layer model. This is just to prove the software is working right. But you see the true model in the middle, the initial model above, and this was just a single shot centered right at the beginning with receivers all the way across. So of course it images well right in the middle only. And that's the loss function reducing over 100 iterations. So the other part of that is that we have this auto diff gradient calculation. And we've got that working for 1D. And as you can imagine, for 2D, we're going to have some memory challenges here because we got like 3,600 time steps here, and that's a lot of history.
All right.
So I think this is where I turn it back to you, sir.
Okay, good, thank you. So it's really running out of time. You know, this is effort we really try to converge this data science and scientific computing together. See, this is really, it's preliminary work at this moment, but we hope we can keep working on this direction. Especially we push the PiSit together with the PiTorch implementation. We think there are a lot of things we can work on that in this research direction. Okay, thank you very much.
Thank you very much for the speakers. We have 3 minutes for questions.
Ready?
Hi. So I had a question about the Rn structure. So you mentioned you use a capital F, which is a complex function. So I wonder, in that function, is it just pure data driven, or has?
No, the answer is no. It's not pure data driven.
Yeah.
This is really just the more formulate the finite different method using the neural network.
So
framework.
using the wave equation, but in terms of the recurrent neural network.
Correct.
Okay.
Yes.
Okay. Thank you.
Yeah.
Questions? Well, I guess I will make one. So you start using PiSit because of reproducibility, productivity, both, or just you look around and that was the easiest path to go?
That's the first answer is because it's a Python solution, which seems nicely merged with this PiTorch. You know, so that's I think the number one thing. Number two thing that has a lot of solvers already built in, and it seems pretty reliable to us, which we tested. We also use a SpecFam, which is that's high performance solution, but we've realized the SpecFam is a Fortran based solution. It's kind of too much effort if you try to merge these two together at this time. So PiTorch and PiSit at this moment seems a reasonable effort to us to be able to merge these two together. So that's really the one that we choose it at this time.
Can you tell how long it took to migrate to this?
To use the PiSit. So first we implement everything ourselves. So we do everything that's spend a lot of time to do the 1D by doing from scratch. We make that work, and then you may talk something how much effort you put onto the PiSit to try to PiSit solution.
So the effort on PiSit, a lot of it was understanding all this elaborate architecture, and that's why the tutorial was good, because it laid the groundwork and you learn it step by step. And then after that, it was the key to these things is designing. They design these matrix operators that implement the Laplacian and all the different aspects of the wave propagation, and so you
But
you
in
just
in
let
terms
it
of
design
time,
those operators, convert them to
ballpark time, it took a month, a week.
weeks. Yeah, I've been working on this for a couple of months now, I guess. So and we've just implemented 2 of the 20 or so solvers.
2 out of 20 at this time. So we still keep going for that work. Still have a lot of work to do to really fully implement
So
that.
we're going to try and ramp it up and actually compute significant problems. Right now, we're obviously just demoing. Right?
Okay, thank you very much.
All right, thank you.